When you think of a precision application, what comes to mind? Some kind of medical device? Sure. Maybe some kind of diagnostic or test equipment? Yes. But maybe also a robotic application or an EV charging design. Yes, as you can see, there are a lot of precision applications out in the world today. But what about powering them? What kind of power requirements should we keep in mind for these specific applications? Well, I'm glad you asked, my friends, because that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Frederik Dostal from Analog Devices and I chat about the what, where, and how of power management for precision applications. We also explore the power requirements for these kinds of applications and the benefits of Analog Devices' silent switcher solutions. And before we get started, don't forget to click that link. There you can find even more information about this topic from Analog Devices. Hi, Frederik. Thank you so much for joining me.
Oh, thank you for having me.
Absolutely. Okay, so Frederik, we're talking all about power for precision applications today. But before we dig into the solutions in this arena, what exactly are precision applications?
Now, this is a really good question because it's not really defined in the industry. Whenever we talk about a precision application, typically we think of an instrumentation type of application. Instrumentation means we're sensing something and measuring something. But precision is needed in any kind of electric system where we are measuring information, right? Analog information mostly. And now to call it a precision application or just a standard type of application really depends on the exact use case. So typically we would call a precision application where we need something better than average, so to say. I know this is not a very precise explanation and answer for your question, but this is what we deal with when talking about precision applications.
That makes sense. So, Frederik, walk me through the power requirements for these kinds of applications.
Yeah, so just before really talking about the power, I'll give you a few examples in the medical industry, in healthcare. When we measure some signals from your body or from other activities, then we need precision, right? And then there are other things like for the power grid of power infrastructure, we also sense if power lines are working correctly, if voltages are correct, and things like that. So, really, from a portable healthcare application all the way to a high power transmission application, we use precision to sense and measure data. So when looking at the power management for these kind of applications, to power these sensors, to power the signal path, the requirements really are all over the place, just depending on what the application looks like. I'll give you another example. Within the healthcare, some applications are actually portable applications. So with a portable application, they would be battery powered. And what do? I mean, you need a battery and some DC to DC conversion that has to be ultra precise, or let's say very, very efficient, and has to help that precision application to run for as long as possible. So to summarize, how do you power these things? But generally, we can say that powering a precision application typically would mean that the power supply has to have a low enough noise that it is generating so that the precision application is not compromised or that the signal path isn't compromised in a way. So we can actually say that some power supplies suit themselves better to power precision applications, while other power supplies do not suit themselves as well. So I think this would be answering your question, right? What kind of power do we need?
Absolutely. Okay, so what kind of solution categories are we looking at here?
So it really depends. When we have a precision signal path, then we have multiple blocks. And these blocks would start from like protection, gain amplifiers, filters, analog to digital converter drive circuitry, and then the ADC itself, the analog to digital converter. There might be isolation, there might be reference voltages the ADC needs that are external. And all these building blocks of our precision signal path need just the right power. And with the right power, I don't mean the right kind of watts and the right voltage, but also when it comes to the kind of noise that's on the supply lines powering these individual signal blocks in the signal chain. And now what we have to do when developing such a system, we would have to look at each individual data sheet of the signal path components and then see what kind of power requirements they have. And then as the next step, once we know that, we will look into different categories of power management ICs that can actually provide a low noise enough power to power these signal blocks of the signal chain. And these kind of categories can be all over the place because the applications are all over the place. So one could be all integrated power supplies with micro modules that have the inductor integrated and some other passive components all integrated in a small, easy to use, simple, but also high feature solution like very low noise, for example. But then there are also isolated power supplies. Some systems need isolated power supplies. That's a different product category that you were asking for. And then, of course, we've got linear regulators or switch mode power supplies. For the linear regulators, typically we would use them for really ultra low noise type of applications. So very often when you have an A to D converter in your precision signal path that has 16-bit or higher, very often people like to use ultra low noise linear regulators without any switching ripple involved. But for many applications, just the category of plain switching power supply regulators is the category that would be used. When we look at a switching regulator, we have some ripple voltage, of course, on the output, on the generated voltage. But some precision applications might not actually mind that there is some switching ripple, because that switching ripple might be at a frequency that's not so relevant for our precision signal path. In other words, if you're looking for a precision signal that is at a low frequency, if there is some switching ripple at a higher frequency on top of that from a switch mode power supply, then that might be filtered out and might not harm or hurt the precision measurement. It's quite a wide and interesting field because the power supplies, the power product categories are also all over the place, just depending on what the precision application needs.
That makes sense. So, when it comes to switching regulators, what kind of parameters should we keep in mind?
Yeah, there are lots of different parameters you can select from or you have to optimize. And for example, the first thing you would do is to start out with the right topology. Switching regulators come in all kinds of different topologies. There's the step-down buck topology, there's a boost topology, there are buck boost topologies, isolated topologies, and so on. So the first thing would be to select a topology. But then also you can select the switching frequency. So of course, every switch mode power supply has some switching frequency, and that can be predefined by the product, or most products actually have the feature to select the switching frequency. And that is one item to select wisely in a precision application to make sure that the kind of switching ripple that comes from the switching frequency is not exactly at the kind of bandwidth that you need in your signal path for your signals. Keep it away from these signals, for example. But there are many other things to consider, like the kind of operation mode. Some switching regulators, when they operate in a low power type of state, they fall back to a very efficient low power mode. And these modes can be like a burst mode or pull skipping mode. That is very good because it saves power. It keeps the efficiency high also when the load condition is at a low load. But the problem might be in a precision application that that kind of burst mode or pull skipping mode might actually generate noise at exactly these kind of frequencies that we look at in our signal path. And so this is something also very important to consider. So this was mentioning just a few of these things, but of course, as in any application, the solution size is important. And ultimately, we don't like to really admit it, but every application is also cost sensitive. So price also does matter as a feature. So it's a lot of decisions somebody has to make when selecting the right switching regulator for a precision application.
Absolutely. So, Frederick, what about linear regulators? So what should we keep in mind here?
I guess we have seen a large transformation coming from linear regulators to switch mode power supplies generally in the industry. But I mentioned earlier that if you have really high precision applications, very often you want to get rid of the switching noise completely in your application. And if you do that, you can still use a linear regulator. And for that, there are some very advanced, good, ultra low noise linear regulators. When selecting one of those, it's the largest thing to look at. The most important thing to look at is really the noise behavior over frequency, low frequency noise, also higher frequency noise that linear regulators have. Once this is taken care of, all the other requirements are important as well. For example, the linear regulator converts one voltage, a higher voltage, into a lower output voltage. And the closer your input voltage is to your output voltage, the more efficient these linear regulators are. But for that, you need a linear regulator that actually can operate when the input voltage is only a little bit higher than the output voltage. It's a very efficient operation mode, but it requires special linear regulators with a low dropout voltage. So, of course, this is an important spec. One other thing with the linear regulators, since generally they are not so super efficient, you dissipate some electric energy into heat, or you generate heat out of it, and that has to be dissipated. And that means for linear regulators, we always have to make sure that the devices can actually dissipate the kind of heat that they generate from the voltage drop that they do. And so dissipating the heat means selecting the right kind of package that is able to dissipate the heat away from the linear regulator. But of course, this specifically isn't only true when powering precision signal path. It is also true in any kind of application where we are using linear regulator.
Okay, so Frederick, let's also talk about power management for these kinds of applications.
Yeah, so with the power management, some things might be important, like sequencing, for example. If we build a power architecture that is powering our signal path application, has different building blocks typically, right? An ADC driver, the ADC, and so on. And in some applications, all these building blocks need separate or different supply voltages or different power rails, voltage rails, so to say. So sometimes it is important to get the sequencing right for all these different power rails. So that is one important thing. But otherwise, when we talk about managing the power, so to say, it does come down to the noise level that is coming from the power supplies. And when we look at the noise levels, there are two different things. We have to look at the conducted emissions of a power supply, but also we do have to look at the radiated emissions of a power supply. Because ultimately, if it's a precision application, it's a low noise application mostly, which means we have to look at all kind of noise that is being generated mostly by the power supply. And so we have to address the different noise sources, so to say, coming from the power supply, the conducted emissions and the radiated emissions. And for both, there are different things that we can do to keep them in check and to reduce them.
Okay, so Frederick, talk to me more about the silent switchers you mentioned.
Yeah, so the silent switches are quite an important innovation that happened a couple years ago. So silent switches, at first when I heard about silent switches, I thought, well, this is just a marketing gimmick, so to say. It's just a switching regulator, maybe with some, wave shaping for the rising edges and the falling edges to make them lower EMI. However, I was not correct. When I learned about the technology, really, I was really amazed at what it does. So the silent switches in a step-down regulator, they would have a setup to split the pulsed input currents in two halves. That helps to reduce the amplitude of the pulsed currents on a trace by splitting them in two halves. But what's also done is these two halves have a symmetrical setup. So we have pulsed current going into the switch from the left side and from the right side at the same time with 50% of the amplitude. Then with the three-finger rule is we have pulse currents on one side, pulse currents on the other side, and the pulse currents generate magnetic fields. And these magnetic fields then cancel each other in a way because one side of the symmetrical setup generates a magnetic field in one direction and the other side generates a magnetic field in the other direction. So the silent switches actually do help dramatically to reduce the radiated emissions that come from any kind of switch mode power supply. And this is really amazing that such a big innovation just happened all of a sudden after people were looking at switch mode power supplies for 40 years, 50 years, 60 years. And then all of a sudden somebody has a really clever idea and it actually does work, so that now a lot of the devices that we release are silent switcher devices. Something important about the silent switches is also we call them silent switches, so of course they're very good for the precision applications and instrumentation type of applications because they have low noise. However, once we generated these parts with the low noise, we realized, well, if you have low noise coming from the switching transitions, then we might as well have much faster switching transitions and still have low noise. So that means we can reduce the switching losses. To have them low is very good because that helps with our conversion efficiency of the power supply. So we could have called these switches also the high efficiency switches, for example. But then we have realized, well, if the switching losses are so low, we might as well switch at a much higher switching frequency and move the switching frequency from, let's say, 1 megahertz to 2 megahertz or 5 megahertz or even 10 megahertz. And when doing that, the inductor becomes really, really small and the output capacitor becomes really, really small. And that helps to shrink the solution size. So we could have called the silent switches also the small solution size switchers. And then these are lower cost, a small inductor, a small output capacitor, or just fewer output capacitors. So we could have called the silent switches also the low cost switches, right? So it's not just helping the noise, it's helping many things in the power supply design. And I think this is why the silent switches are really exciting. And we come up with more features and more advanced family members of the silent switches. This is first generation, a second generation, and a third generation, and this is really the way to go. And we actually do see also, we really found gold because the best, I guess, sign is that you really stumbled across something meaningful is when competitors are copying you. This is a nice proof of excellence, I guess.
So, Frederick, what specific analog devices solutions would you suggest using here?
There are many, many different parts available that are great to use in precision applications. But there's one device that is really new and showing another innovation that has not existed a year ago. So we have some of the micromodules, like the all integrated power supply devices that have the inductor also integrated into the part itself, so to say. Some of these devices, we have just come out with a solution that uses a shielded package. So while silent sources are low noise to begin with, using them within a shielded package of the micromodules is reducing the very, very little radiated emissions that they still have another way additionally. So that means that then the electric field emissions of these first parts that we have released with the shielded package, the electric field emissions get lost in the noise floor of electric field when you do electric field sensing outside of the package, which is amazing. That pretty much means we have solved the problem of radiated electric fields. Of course, besides the electric field, there's also the magnetic field. And with the magnetic field, when we measure this with a near field sensor, we can still detect it, but it's a lot lower than if you use a non-shielded package for these devices. So if you use ultra low noise switch mode power supply parts to power your precision application, and you still see some room for improvement, my suggestion would be to use a micromodule that has a shielded package. And then try this application, because this is the lowest noise you can get today in the industry.
So, Frederick, what about help with the power tool chain? How can analog devices assist me in this case?
Yeah, I think the power tool chain is really an important thing. Just tool chains in general. I remember like when I started working in industry maybe 25 years ago or 30 years ago, we didn't have all these tools. And the problem really was that people would have to write down formulas and design with a pen and paper. But why having to reinvent the wheel every time you do a design? So tools exist nowadays. We're very happy these tools exist. And Analog Devices has great tools for the signal path itself for precision applications. So we have the ADI Precision Studio, which is a nice signal path tool. It includes an analog filter wizard, and then you can export everything into LT Spice. So I think this is a great signal path design tool chain. But what about the power? So that's the question that you have asked, really. We also by now have a complete power management tool chain. And the power management tool chain isn't just LT Spice, that a lot of people know, obviously, but it consists of LT Power Planner, LT Power Cat, LT Spice, LT Power Play, and even LT Power Analyzer. So now it's a complete tool chain that covers every aspect from just a block diagram generation tool with the LT Power Planner through LT Power Cat, which is a calculation tool for the power supply. And within the power calculation tool, you can already look at the Bode plot of the power supply to see how stable the power supply is and so on. And then also you can look at output ripple voltage, and you can design a filter on the output side to reduce the conducted emissions on the output side, to reduce the output ripple voltage. You can also design an input filter for the power supply, all within LT Power CAD. And then LT Spice, of course, a great simulation tool once we've done the calculation in LT Power CAD. And once we have double checked with an LT Spice that the power circuit is working really well, you can do a simulation with the power supply and the signal path component all in one Spice simulation. And once you are happy with that and you build your hardware, you can use the LT Power Analyzer, which is a full, let's say, power management measurement setup that helps to generate Bode plots to make sure that the circuit is really stable and that the power supply is reacting to line and load transients in a nice, fast manner. And all these tools work together. So that's why I think we're at a very nice point in time when it comes to power supply tools in general in the industry, that it's not just one simulation tool, it's really a complete tool chain. And that's making the life so much easier for the design engineer having to come up with an optimized precision electronic design.
Excellent. Well, Frederick, I think that's all I have time for today. Thank you so much for joining me.
Well, thank you for having me. It was a great pleasure for me. Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Analog Devices. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.